In approximately 5 billion years, the hydrogen reserves in the sun's core will be depleted, and the star will begin burning hydrogen in its outer layers, transforming into a red giant. Its luminosity will increase significantly, the core will contract, and the outer envelope will expand. This process will continue for billions of years, accompanied by the gradual loss of the sun's mass. As a result, the orbits of the planets will begin to increase. At the final stage of its transformation into a red giant, the sun will expand so much that it will extend beyond Earth's current orbit. Its radius will reach about 1.2 astronomical units. Initially, as the sun expands, the moon's orbit will slightly increase, and its orbital period will lengthen by a few days. However, the streams of material ejected by the dying star could drastically alter the moon's orbit and even force it to collide with Earth. If the moon's perigee distance shrinks to 18,470 kilometers, it will match Earth's Roche limit. This will trigger intense tidal interactions capable of destroying the moon. Its fragments would form a ring system around Earth, while some material would fall onto its scorched surface as a meteor shower. However, over time, these rings would dissipate, as has happened in the distant past. The Earth-Moon system is a binary system, orbiting a common center of mass located about 1,700 kilometers from Earth's center. Therefore, the moon's disappearance would be catastrophic. Orbital motion could change, the planet's rotation might accelerate or slow down, leading to instability in Earth's mantle and potential shifts in its magnetic poles. Any remaining life forms would face new climatic and geological disasters. Now, let's return to the main scenario. Not only planetary moons are subject to instability, entire planets themselves could also be thrown from their usual orbits. Computer simulations indicate that in the distant future, planetary collisions are possible. These calculations are extremely complex. A home computer would take about 200 years to complete such a task, while a supercomputer would need several months. Scientists have had to focus only on modeling the orbits of the 8 major planets, as accounting for every possible scenario involving millions of celestial bodies is impossible. Astronomer Jacques Lascar studied 2,500 possible evolutionary scenarios and selected the most catastrophic ones. He then conducted additional simulations of several hundred scenarios based on the most dangerous ones. According to these models, the gas giants will remain in their current positions, while the terrestrial planets may undergo significant changes. Mercury is considered the most unstable object. Due to its low mass, it is the easiest to knock off its usual orbit. Its orbit is already elongated, and in the future, it may become so distorted that it intersects with Venus's orbit. Additionally, Mercury is in an orbital resonance with Jupiter. Their orbital periods are related by small whole numbers. This periodic gravitational interaction can either stabilize Mercury's orbit or make it more chaotic. One scenario predicts that 90 to 100 million years after Mercury's orbit destabilizes, it could collide with Venus. If this happens head-on, the catastrophe will remain localized. However, in a glancing collision, Mercury could be ejected either toward the Sun, where it would be consumed, or toward Earth, like a billiard ball. The probability of this event is only 0.6%. There are also other, less likely scenarios. In one model, Mars completely leaves the solar system in 820 million years. And 40 million years later, Venus collides with Mercury. In 196 models, planetary collisions occurred, with 18 predicting a catastrophic encounter between Earth and Venus, while 29 suggested an Earth-Mars collision. In rare cases, Jupiter could fling Mercury toward Mars, causing it to ricochet toward Earth. In another scenario, Mars alters Venus's orbit, ultimately leading to its collision with our planet. Such chaos has already occurred in the early history of the solar system. According to the NICE hypothesis, the planetary system looked different in the past. Jupiter, Saturn, Uranus, and Neptune were located closer to the Sun, within a range of 5.5 to 17 astronomical units. The outer region contained a dense disk composed of icy and rocky planetesimals with a total mass of about 35 Earths. Gravitational interactions forced the giant planets to alter their orbits. At some point, Jupiter and Saturn entered a 2-to-1 resonance, which led to changes in their orbits. Saturn began moving outward, interacting with Uranus and Neptune. Their orbits became more elongated, and they may have even swapped places. As the ice giants intruded into the outer disk region, they triggered a massive redistribution of material, sending some of it to the far reaches of the system, forming the Oort cloud. Another portion of planetesimals was ejected into the inner solar system. This caused a period of intense late heavy bombardment, leaving enormous craters on the Moon and Mars. For Earth, this period was crucial in the history of life. Being close to the Sun, it could not retain a large number of volatile compounds, including water. However, as a result of the bombardment, numerous water-rich asteroids and comets struck the planet, leading to the formation of oceans and creating conditions for the emergence of life. Thus, the chaotic dynamics of the solar system played a key role in shaping our planet's past, and in the distant future could lead to catastrophic changes, including potential planetary collisions.